Imagine you're cruising at 30,000 feet, looking out the window at the vast, peaceful expanse of clouds. Suddenly, the wings of your aircraft start spewing massive plumes of white liquid into the void. It doesn't just drip, it erupts. To a passenger, it looks like a catastrophic leak. It looks like a disaster in progress, a terrifying mechanical failure that could end in tragedy. Your mind immediately jumps to the worst-case scenario: an engine explosion, a ruptured fuel line, or a mid-air emergency. But in reality, what you're witnessing is one of the most calculated, high-stakes engineering maneuvers in aviation. A maneuver that, despite its frightening appearance, is actually the primary reason you will reach the ground safely. Every year, thousands of tons of volatile jet fuel are intentionally dumped into our atmosphere. It's an incredibly expensive process. It looks absolutely terrifying to the uninitiated, and to the untrained eye, it seems like an ecological nightmare. But why would a highly trained pilot throw away $50,000 worth of refined kerosene just minutes before landing? Is the aircraft broken beyond repair? Is the runway too short for a standard approach? Or is there something deeper, something hidden in the unforgiving laws of physics and structural integrity? Today, we go inside the heart of the turbine and the intricate veins of the airframe to uncover the impossible physics of the fuel dump. We're stripping back the aluminum skin to see the valves, the high-pressure pumps, and the terrifying math that dictates a simple, brutal choice for the flight deck: dump the fuel or face the fire. To truly grasp the necessity of this system, you have to understand a concept engineers call the weight gap. It is the fundamental struggle of every aerospace designer. A modern long-haul aircraft like the iconic Boeing 747, the massive Airbus A380, or the workhorse Boeing 777-300ER is essentially a flying fuel tank with wings attached. At the moment of takeoff, these machines are at their absolute structural limit. A fully loaded 777 can weigh nearly 350 tons. To get that much mass off the ground and sustain it for a 14-hour flight across the Pacific, nearly one-third of that total weight is nothing but Jet A1 fuel. It is the lifeblood of the journey, intended to be burned off slowly over thousands of miles. But here is where the engineering trade-offs become dangerous. While the wings are masterfully designed to lift that massive weight into the sky using the sheer thrust of the world's most powerful engines, the landing gear is a completely different story. The maximum takeoff weight is a testament to the power of lift and aerodynamics, but the maximum landing weight, or MLW, is a testament to structural impact and the limits of materials science. The landing weight is significantly lower, sometimes a staggering 100 tons lower, than the takeoff weight. Why is this gap so large? Because landing isn't just a gentle touch on the asphalt, it's what pilots and engineers call a controlled collision. When a heavy jet hits the tarmac, even in a perfect landing, the kinetic energy doesn't just vanish. It must be absorbed instantly by the hydraulic struts, the massive rubber tires, and the primary wing spars. If the plane is too heavy, the physics of momentum become destructive. The landing gear struts won't just compress, they will reach their limit and transfer that energy into the airframe. In a worst-case scenario, the gear will punch straight through the wing structure like a hot needle through butter, rupturing primary fuel lines and causing an immediate catastrophic structural failure. In engineering terms, if you land heavy, you risk a hull loss. The aircraft becomes a write-off, too expensive to fix and far too dangerous to ever fly again. This is why the ability to shed weight quickly is not just a secondary feature, it's a critical survival mechanism. History shows us that in a sudden emergency, a pilot forced to return immediately after takeoff is trapped in a mechanical paradox. They have too much mass to stop safely. An overweight aircraft becomes an unstoppable projectile that a standard runway simply cannot contain. This is where the jettison system becomes a lifesaver. Interestingly, not every plane can dump fuel. Short-haul jets like the Boeing 737 or Airbus A320 don't even have this equipment. They are light enough to land safely even with full tanks, or can simply fly in circles to burn off the excess. But the transoceanic Titans carry so much fuel that burning it off would take hours they don't have. They rely on a mechanical heart hidden beneath the floorboards. Powered by high-capacity override pumps, the system opens nozzle valves at the wingtips, far from the scorching engine exhaust, when the pilot activates the guarded jettison switch. Fuel is pumped out at nearly 2,500 pounds per minute, emptying a backyard swimming pool in under 60 seconds. Specialized nozzles atomize the liquid into a fine spray. This is critical. If fuel came out in a solid stream, it could coat the fuselage or be sucked into the engines. Instead, it becomes a microscopic aerosol mist designed to vanish into the atmosphere. Is it raining kerosene on your house? The short answer is no. Pilots are strictly regulated by international procedures, usually maintaining at least 5,000 feet of altitude and staying clear of populated areas. At these heights, cold, thin air and high-velocity slipstreams break droplets down into particles smaller than a human hair. They evaporate and disperse as vapor long before touching the ground. While not eco-friendly, it's a necessary calculation to prevent a certain disaster on the runway. But what if there's no time? If an engine is on fire 5 minutes after takeoff, the pilot faces every aviator's nightmare: the overweight landing. This requires surgical precision. The sink rate must be kept incredibly low to minimize impact, but a heavy plane naturally wants to fly fast, making the approach a dangerous tightrope walk. If they hit too hard, tires disintegrate and carbon brakes, absorbing millions of joules, can catch fire, glowing an incandescent cherry red at 800 degrees Celsius. After such a landing, the aircraft is grounded for weeks of intensive X-ray inspections to find microscopic stress fractures. The fuel dump system exists specifically to act as a buffer against this impossible crushing weight. It is a testament to the safety-at-all-costs nature of aviation, a system built for scenarios we hope never happen, respecting the raw physics of mass and gravity. Next time you see those white trails erupting from a wing, remember, you're not looking at a failure. You're looking at a masterpiece of emergency engineering. It's the weight of a skyscraper being shed in real time, ensuring that hundreds of souls can touch the earth safely and return home. So, what do you think? Is the environmental cost of dumping fuel still acceptable, or should engineers focus on gear that can handle any weight? Does understanding the weight gap change how you feel when you hear the engines roar on takeoff? Let us know in the comments below. And if you want to continue exploring the hidden systems of the world's most complex machines, hit that subscribe button. The sky is full of secrets, and we are just getting started.